All right, welcome to The Explainer. Today, we're diving into something pretty wild, a new way of looking at reality itself. It's a theory that tries to build our entire universe, from the tiniest particle all the way up to the whole cosmos, from just a handful of simple rules. And it all kicks off with one big, mind-bending question.
What if everything around us, everything you see and experience, is just the answer to an unbelievably complex calculation, a cosmic computer program that's been running since the very beginning of time? Now, to get our heads around this, we're going to borrow an idea from computer science, the famous P versus NP problem, and use it in a way you've probably never seen before.
So stick with me here. In computer science, P versus NP is a huge unsolved question. But for us, let's think of it as an analogy. Imagine NP represents the infinite potential of the universe, every single possible path it could have taken. And P is the one single concrete reality that we're actually living in. The real question then becomes, how do we get from that infinite ocean of NP possibilities to our 1P reality? What's the process? This quote really gets to the heart of the theory we're exploring. It frames reality not as a thing, but as a process. A kind of computational engine that takes all the chaos of infinite potential and, moment by moment, calculates the ordered, structured reality that we see around us. So, if the universe is a computer, you have to ask, what's its source code? So, if our reality is a calculation, what's it written in? Well, this theory proposes that the source code of the universe is, believe it or not, surprisingly simple. It's all built from just two fundamental ideas that give rise to, well, everything. First things first, the theory says space isn't just empty. Nope. It's made of these fundamental units, almost like pixels on a screen, and they're called nodes. Every single node has one core property, which is called information mass. Now think of it this way. A node that's describing something simple, like a patch of empty space, has very low information mass. But a node describing part of a really complex particle, it has super high information mass. It's basically a measure of how much complexity is packed into that one tiny point. And this right here is the single rule that tells all those nodes what to do. The theory calls it the master curvature equation. Now, don't worry, we're not going to do the math. The big idea is what's important. It's a rule that tells spacetime how to bend and curve based on two things: the information packed inside the nodes and the geometry of the space around them. This is the engine that runs the whole simulation. So let's just pull that equation apart for a second. It's really just two pieces. The first part is the informational term. Now this is a wild idea. It's saying that pure information, just order and structure itself, can actually bend spacetime. A highly ordered region curves spacetime differently than a chaotic one. The second part is the geometric term, and this is a bit more familiar. It describes how the information mass of distant objects creates that curvature we call gravity. So reality is literally being shaped by both local order and distant mass. A simple rule is one thing, right? But can it actually build anything we'd recognize? Well, let's put this reality engine to the test. Let's see if we can use it to construct something as fundamental to our world as a proton. According to this theory, a proton isn't just some static little ball. It's a dynamic, stable system. They call it a dynamo. It's made of three smaller particles called quarks, specifically two up quarks and one down quark, all bound together by the rules of that master equation. Their constant dance and interaction create this incredibly stable, self-sustaining structure that has a net positive charge. It builds a proton. Okay, now this is where it gets really interesting. A core prediction just pops right out of this model. As you get a particle moving close to the speed of light, the vacuum of space itself starts to create a kind of drag, stopping it from going any faster. So, what happens if you keep pumping in energy? Where does it go? The theory predicts that the energy can't increase speed anymore, so it has to get converted into the particle's internal state. It boosts its information mass. And what is that? That's E equals mc squared, emerging directly from the model's first principles. So the model can build one proton. That's cool, but how does it hold up under, extreme pressure? This is the ultimate test. A simulated proton-proton collision at the same insane energy levels as the Large Hadron Collider. This table compares the simulation's predictions for what particles should get created against the actual real-world data from CERN. Let's see how it did. 99.9%. That's the accuracy of the prediction. For key particles, like the W and Z bosons, the simulation matched the real-world experimental data from CERN almost perfectly.
I mean, just think about that. From those simple starting rules, the theory correctly predicted the outcome of one of the most complex, high-energy experiments humans have ever devised. Okay, so the model clearly works on the subatomic scale. But to be a real theory of reality, it has to work at the largest scale of all, the entire cosmos. If these rules are truly fundamental, they shouldn't just build a proton, they should be able to build a whole universe.
In this model, the universe didn't just expand, it evolved. It passed through a whole series of epochs, where spacetime itself had different dimensions and different properties. The theory suggests it started as a super simple 1D structure, then transitioned through various phases as it cooled, constantly solving for a more stable state, until it finally settled into the universe we know today.
Now here's the ultimate test for any cosmological model. Can it reproduce the oldest light in the universe? We're talking about the cosmic microwave background, or CMB. It's the faint afterglow of the Big Bang, or in this theory's case, the Big Pop, and its pattern holds all the secrets of the early universe.
And the results are just stunning. The theory was used to run a full cosmological simulation, generating a prediction for what the pattern of the cosmic microwave background should look like. And as you can see on this chart, that prediction is a near-perfect match for the real observational data from the Planck satellite. The same rules that build a proton can also build a cosmos.
So let's bring this all home. We've seen how a few simple rules can build a proton and recreate the entire cosmos. So let's get back to where we started. Is the universe solving a math problem?
The theory gives us this beautiful conceptual answer. It says that the single concise reality we experience, that's our P, is the result of the universe constantly processing its own infinite potential, the NP. And what's the mechanism for this calculation? It's time. Through the arrow of time, the universe collapses chaos into order, potential into actuality, literally solving for its own existence moment by moment.
And that brings us to our final thought. This theory offers a powerful new way to see existence as a grand computational process. But if the universe as we know it is the solution, an elegant answer computed over billions of years, it leaves us with one last profound question to ponder. Thanks for joining me on The Explainer.